So requirements are super duper important. I'm going to spend quite a bit of time on it. So sources of requirements. First, I think I should motivate requirements. Requirements are the framework for a design. They are like the bedrock, the stability offered to a design. So a really good set of requirements can yield to a really good design. Sorry, something happened. Okay. So yes, requirements are the bedrock for a really good design. Explicit, well-defined requirements lead to a well-designed spacecraft. So let's go over sources of requirements. Stakeholders, that's, as a reminder, you, me, NASA, we can come up with some system and mission requirements. For programmatic requirements, I listed having a $2,000 budget for allotted senior design funds. Another programmatic requirement is that the schedule is bound by our class time together. Our mission classification is another programmatic requirement. So we are a low priority and high risk project, which allows for us to take on more risk than other high priority missions. Some constraints for programmatic could be the customer's payload. Say we were tasked by the Los Alamos National Lab to fly a certain payload that they are interested to see fly in a certain orbit to observe a certain phenomenon. We would have to design around that specific payload and work with those specific scientists. Another set of requirements can come from launch providers. We'll most likely go through NanoRacks, a launch provider, and they have a suite of structural, power, and thermal requirements, constraints, and information that we need to incorporate into our design. External standards and requirements include documents like NASA GEVS, which I looked up and made sure to include this time. NASA GEVS stands for General Environmental Verification Specification, from which we tailor our environmental test programs. The major test areas covered by the GEVS includes mechanical, thermal, and EMC, as well as more general requirements for planning, tracking of the verification programs. Institutional constraints can be the types of collaborators or vendors that we work with, brought on by the type of contracts that we can accept. The technical requirements are a ball game in themselves. They are immense, and what we're going to, everything else that we just talked about, that's like the context and things that we should think about. But in this class, I kind of want to stress the more technical side. Technical requirements are nested and refined from the system to a subsystem to individual components. At some point, you're going to have to allocate or derive requirements. So here you'll see a flow of the way requirements come about. So we're up here where we're creating mission objectives, but soon you'll have to create mission requirements, and then you'll have to come up with system functional requirements, break it down even more to system performance, and then subsystem function and performance requirements, and then on to components. So you can see there's an action of allocating requirements and deriving requirements. So requirements allocation is the act of decomposing higher level requirements and assigning them to lower level functions, which is that process that we just went down, the flow down. All requirements of the top level functions must be met by the aggregate of those for all lower level functions. Functional analysis and allocation of the systems engineering process is where requirement allocation occurs. Requirement allocation is often difficult to prove when an upper level performance requirement is achieved through a number of derived requirements. For instance, system accuracy is composed of a derived functional attributes that in sum determine its value. Consequently, it is extremely important that higher level requirements are allocated properly, but also that traceability to the originating requirement and rationale for the allocation be recorded and maintained. Derived requirements are requirements that are not explicitly stated in the set of stakeholder requirements, yet is required to satisfy one or more of them. So they're kind of like fill in the gap type requirements where it's not explicitly stated, but it is needed to, glue the system together. They also arise from constraints, consideration of issues implied but not explicitly stated in the requirements baseline, factors introduced by the selected architecture, and the design itself. Derived technical requirements are those that result from the analysis and allocation of technical requirements to logical functional architectures that are developed as part of the requirements analysis process. And then there was a question about, can requirements include constraints that came from other tested satellites? So yes, I think I can give you an example of this. There's something called space heritage where aerospace engineers like to mitigate risk. And one way to mitigate risk is to use components that have flown in space and have been proven to work in space. So if, say, a satellite has flown a component you're interested in using, and this component is in a suite of solutions that you're considering, it can be very likely that you will choose the component with space heritage over the other ones, even though their other performance metrics are pretty similar. The opposite can be true, where some satellites have flown a component and it absolutely did not work, so a constraint could be to not use that component at all. Another soft thing that I think HSFL has been doing and other satellite groups is that working with vendors, you have to have a relationship with vendors or collaborators, and some teams are easier to work with, some not. So that can be an institutional constraint from previous satellite missions. Okay, so let's talk more about requirement allocation. Here on the right is a diagram of how you could break down high-level science pointing requirements to, so this is mission level, to system level spacecraft and ground requirements. The spacecraft bus can then be broken down into attitude determination requirements, which is a subsystem. And then its performance in the components can be allocated into total gyro to star tracker error, or attitude estimation error, which is an algorithm that you have to write. And then those component requirements can be broken down even further to individual characteristics of the component that you're looking for. So I just walked through an example, but formally, regardless of what it is, the three key steps in performing functional analysis are to translate top-level requirements into functions that should be performed to accomplish the requirements, decompose and allocate the functions to lower levels of the product breakdown structure, and then identify and describe functional and subsystem interfaces. Oh, there was a question. When there are opposing requirements or constraints, how does the systems engineer choose which ones to keep and which ones to discard? I think that's really tricky, and there isn't one answer for this. It depends on the team. When an engineer faces opposing requirements and constraints, there has to be a negotiation that happens. There has to be some compromise. So this opposition or conflict would move up the chain where you're talking within the level that the requirement is at. If it's a component level, then maybe you have to resolve that within your team, your subsystem team, with your subsystem engineer. If that cannot be resolved, then you keep moving upwards. So then the subsystem engineer can bring it up with the spacecraft systems engineer. If the spacecraft systems engineer cannot resolve it, then you go to the trio, where you have to maybe compromise with your chief scientist or program manager to like spend more money and like throw money at a solution, or to ask that the chief scientist be more lenient with pointing, for example. Hope I answer your question. Okay. Writing good requirements. So I was talking about the structure of requirements and the motivation for why, but how do you implement good requirements? We can go over some language. So requirements are written statements. So we're going to go over the use of correct terms. As I alluded to before, shall is a hard requirement, but if you use words like will, they are facts or declaration of purpose. And then should is softer, it's a goal. There are different types of requirements like personnel and product. And then the next slide will also have different types of requirements. A personal requirement, for example, is the responsible party shall perform such and such. Another language specification that I'll just emphasize here is using active terms instead of passive verbs. A product requirement is probably the requirements that you'll write most of in this project. They come in the form product ABC shall XYZ. So shall verb followed by a description of what should be done, and hopefully you put numbers in. Numbers with units. Product requirements should be complete with tolerances for qualitative and performance values. So I think some of you, I saw numbers in your mission objectives, and that made me really excited. That is very good to do. Okay, and then lastly, for product requirements is the requirement free of implementation. So the requirement should be a goal. It should not be the way that you do something. Avoid that as much as possible, because a goal can be done in many different, or a goal can be achieved with many different methods or implementations. Example product requirements can be the system shall operate at a power level of 14 volts and 0.3 amps. The software shall acquire data from the structure shall withstand loads of 1360 newtons in the axial direction. The hardware shall have a mass of 1.33 kilograms. Let's see, some questions. What are some examples of non-negotiable constraints versus softer constraints versus a non-constraint requirement? So I think that this question is answered by the use of correct terms, where non-negotiable constraints can be that shall kind of requirement. A softer constraint will be that will, and then a non-constraint is should. Although non-constraint is kind of a paradox in itself. Now, examples of this. Non-negotiable constraints can be externally imposed. So when I was talking about the structure withstanding a load of 1360 newtons, that is a specification brought on by NanoRex, our launch provider. And those, I mean, we are totally dependent on our launch provider. We have to make them happy. So that's not something that they're going to negotiate upon. Softer constraints can be let's see, will statements. Could be the attitude determination system will use this vendor's IMU. It may or may not happen. I think you could choose a different solution. I don't think that was a great example, but hopefully we can together, when you're coming up with your constraints, we can have that discussion more. Okay, and then someone said to some requirements, I appreciate how explicitly they are stated. Is this necessary? Yes, 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 yes. Explicit is so good for requirements. So yes. Okay, more rules or guidelines for writing good requirements. You want your requirements to be grammatically correct. There are so many times where a misplaced comma or a missing comma can produce ambiguity. Like, what is that book? A Panda Eats, Shoots, and Leaves. And the cover of the book shows a panda with a gun. The Oxford comma causes a lot of confusion. Anyway, so that's its own path of language affecting requirements. Requirements are free of typos, misspellings, and punctuation errors, complies with the project's template and style rules. Requirement is stated positively. So for example, this checklist is a soft constraint where these are good guidelines. Other things, requirements do not have to be finalized when you're initially developing them. So you'll see here one of the rules is the use of to be determined values should be minimized. You can have to be determined when you're first coming up with requirements. Requirements should be as good as it can be upon the initial first pass, but there are going to be analyses that you do during your design process that clears up what the requirement really should be. So then when you figure out what a better number should be, you can go back to your requirements and modify them, replacing to be determined with a number and a unit for performance, for example. I understand that it can be a little bit like a chicken and egg problem where what comes first? And we log those kind of technical rationale. Like if you were to do analysis and go back to your requirements, in your requirements log, you'll write like the date of the change and the reason why you changed it. Okay, and then requirements are located in proper section of the document. I have templates for requirement tables, so this should not be a problem. Requirements validation checklist. When you're writing requirements, you can go through this simple checklist of making sure that it's clear, complete, compliant, consistent, traceable, correct, functional, list performances, list interfaces, can be maintained, that they're reliable, verifiable, or testable, and data usage. I don't know how to describe that one, so I'll just skip it. Okay, verifying requirements. Here is a sample table of a requirements verification matrix, and then on the right is a verification test report. So this is something you will see in a template that is in the template folder, where the requirement has a certain number. It's like a shorthand way of referencing that requirement. It can be drawn from a certain document. And then you can copy paste some of the text. Then you have your actual requirement, the way that is possible to verify it, or the goal for verification to prove that you've met the requirement. Then you have the verification method. And then you have all of these other things about like where you're going to test it, when you're going to test it, so on and so forth. And then here's a sample of verification test reports where you're actually doing this step, the verification success criteria and method. Okay. So questions about requirements. I answered some of them. The ones left unanswered are, I'm assuming that we are held responsible for all of the design processes. Are we pretty much just the middleman between stakeholders and the engineers working on the satellite? Oh gosh, this noun, I'm not remembering what this noun is. I think I answered the non-negotiable constraints. Okay, I'll answer this one about rovers on the moon and then circle back to design processes. The last 2 rovers sent to the moon. Oh, actually, class, if you wrote this question, can you please clarify what they are, if you can remember? Okay, the last 2 rovers sent to the moon didn't survive landing. Do you think their respective space agencies still lack the knowledge to do so? Or did they fail to check all the boxes in system requirements and testing? I mean, I think they're one and the same. I think that failing to check all the boxes in system requirements can be part of the lack of know-how to successfully carry out a mission. I think there are many different factors if a mission is not successful, whether it comes in the writing requirements or the design implementation or the integration and testing. Yeah. But you know what? Having bad requirements can be a reason why a mission fails. Okay. So I'm gonna pause